Today we're going to talk about definite integrals. So here I'll draw a curve like this, and this is point A and this is point B. So this is f of x, and we're measuring the integral from A to B of f of x, which is basically measuring the area underneath the function from point A to point B. That is what a definite integral is. It's finding the area of a function between 2 points, point A and point B. So if I evaluate this function, what I get is I get antiderivative f of x from B to A. So this is the notation of this is a change notation. So the change notation basically is saying from B to A, which is equal to f of B minus f of A. Sort of like how delta works in equations, like delta t is equal to t final minus t initial. This case we have final being B and initial being A, and delta t is just the antiderivative of f. So say we have the integral from 1 to 2 of x dx, right? So that's just, so the graph of this function is just like that, and this is 1 and this is 2. So we're just trying to find that area right there. So we'll call this area A. And so A is equal to this integral from 1 to 2 is equal to this integral. The integral from 1 to 2 of x dx. Y is equal to f of x, and we'll say f of x is equal to x. So our function, so y is equal to f of x. Our function, so y is equal to the function f, and our function f in terms of x is x. And so the area from 1 to 2 of we'll just put it in function notation, of f of x dx is just equal to the integral from 1 to 2 of x dx. And so the antiderivative of x is 1/2 x squared. And so this means that we're going from 2 to 1, which means that it's 1/2 2 squared minus 1/2 times 1 squared, which is equal to 1/2, 2 squared is 4, 4 divided by 2 is 2, minus 1 squared is 1, 1/2 is equal to 3 over 2, so 3/2. So A is equal to 3 over 2. And that's how you would find an area using a definite integral. What is the definition of a definite integral? Say we have the following curve. From this point, from point A to point B, right? And so we want to find the area underneath this curve. So how would we do that without using an integral? Well, we would just take a rectangle. We would just take a bunch of rectangles. I would say equal size. And just measure the area of each rectangle to approximate the area underneath the curve. Right? So basically, the more rectangles you have, the closer your approximation is to the actual answer. So basically, we add up the areas of all these rectangles. So the area of this rectangle, so say we have n rectangles. So we'll call this 0, and we'll say that this is point P. Instead of A and B, we'll just do 0 to P. Okay? So from 0 to p, we have n rectangles. Okay? And so n is basically the number of rectangles we want to do. It can be 1, it can be 2. So what is the area of this rectangle? Well, the distance, each rectangle has an equal width. So the width is equal to, well, it's just the distance, the total distance, p, divided by the number of rectangles, n. So the width is p over n. Of each rectangle, the width is p over n. For each rectangle, the width is p over n. Or if we were doing a to b, the width would be a minus b over n. So what we're just going to do from 0 to p. So the width is p over n. Instead of p, we'll actually just do c. C is nicer. C over n. C over n. And this distance from 0 to c is delta x. So the width is delta x over n. We'll just call it p again, just for, okay. Because c is going to show up later. From 0 to p, the width, that distance is delta x, and so the width is p over n, which is also delta x over n, because we're going from 0 to p. If we were doing a to b, the distance would still be delta x, but the width would also be b minus a over n. So the width would be b minus a over n, which is also delta x over n. Alright? So, what is the height of each rectangle? Well, the height of each rectangle, since each of these rectangles is touching on the right point. Each top right vertex is touching this curve. So that would mean that it's a. So this first rectangle would be a plus the width, and then the height is so this is f of x. So the height is equal to just its value after you add its width. So the height is just f c. So c is the rectangle number. It is the number of the rectangle. And the c times delta x over n. So that's the height, is f of c times delta x over n. So if that's the height and the width is delta x over n, all we need to do is just do the sum of all these rectangles. So we're going to use sigma notation, which is sum. Sigma from I is equal to 0 to n, the number of rectangle, not 0, 1, my bad. From I is equal to 1 to n, we have f, we have the width, delta x over n, we have the width, delta x over n, times the height. So then we just do the area, times the height. F of c times delta x over n. So c is just a counter. So c stands for counter. We start with 1, then 2, then 3, then... So c is really just I, because it's our counter. So it's I times delta x over n. So now we have our function, like that. So since c is a counter, and I is also counting from 1 to n, then we can just replace c, the counter, with I. And so now, after I explained, so now I've explained that. Now, what is this? Does this matter? Well, what if we wanted to use an infinite number of rectangles to get the closest possible approximation of the area? Well, that's just the limit, as n approaches infinity, of sigma I is equal to 1 to n, delta x over n, times f of I times delta x over n. Like that. So now that we know this is just the definition of an integral, of the definite integral of this. So this is actually equal to the integral from a to b of f of x dx. So basically the sum from this point, from these 2 points, as we get an infinite number of rectangles to approximate the area, then we have the definition of a definite integral.